Hello everyone and welcome to our 6th mini lecture in the opioid series. This time we're going to be talking about opioids and tolerance as well as withdrawal. So first, tolerance. This is, as we've talked about in previous units, the diminishing effect of a drug with repeated use. Specifically talking about opioids, we can get cross-tolerance among different opioid drugs. So using one opioid drug like morphine will increase your tolerance for heroin or something similar. Because these drugs act on similar mechanisms and are metabolized by similar means, tolerance in one drug will promote tolerance to the family of drugs. What we see is often the sensitization of craving or desire, the wanting component of drug use. So that becomes stronger with repeated uses, while the high, so the subjective euphoric liking portion of the drug using experience remains unchanged or decreases as tolerance develops. So while a user might not like the drug as much after repeated uses, their craving and desire to use can sensitize and increase over time. So speaking about these withdrawal symptoms specifically, there's a wide array, as you can see on the graph there on the right, that are sort of opposite compensation reactions for the acute action. For example, opiates are well known for their analgesic properties, their ability to reduce pain perception, and a withdrawal sign is pain and irritability. Likewise, these produce euphoria, but withdrawal can produce dysphoria and depression. You're going to see a pattern that a lot of the withdrawal symptoms are sort of like the opposite of the acute effects. So physical dependence is this neuroadaptive state in response to the long-term occupation of opioid receptors. When I say neuroadaptive, I don't mean adaptive in the sense that it's a good thing that promotes your survival. I mean it's adaptive in the neurons adapt to the changes that you are subjecting them to. So when a drug is no longer present, the cell shows a functional rebound where it sort of overshoots its basal levels and starts sort of doing the opposite of that withdrawal state. And that might not make a lot of sense right now, but we'll show it a couple of different ways. So the withdrawal symptom is sort of the slingshotting back of the acute effect. So for example, opiates can produce relaxation and sleep, and withdrawal from those can produce restlessness and insomnia. We'll give it some more in-depth examples at sort of a cellular level of how this is working as we continue. So opioids depress the central nervous system, so the withdrawal state is hyperactive. And what I mean by that is if you think back to when we were talking about the opioids and their receptor subtypes, all of them are inhibitory with regard to cyclic AMP synthesis and the opening of potassium channels, so they're an inhibitory transmission. So the compensatory state is going to be sort of a hyperexcited type state. So because of those changes that have taken place, when you have a loss of that inhibitory opioid action that your body has become accustomed to, the state it's been put in to compensate for that will leave it in a more excitable state. And we'll talk about that in a different way just here. So severity and duration of the both acute effects and the withdrawal effects are influenced by many factors, in particular the drug that's used. So for example, morphine withdrawal peaks 36 to 48 hours after the last use, and it's a rough peak and drop, whereas methadone peaks gradually over several days and increases rather gradually over several days and decreases over several weeks. You can see over here on the right we have graphed both the intensity of the drug effect and the intensity of the withdrawal. You can see these kind of mirror one another. Drugs that reach high saturation quickly and produce really strong effects tend to have a similarly sharp and unpleasant withdrawal curve, whereas methadone produces a much less intense drug effect and also a much more gradual withdrawal, as you can see here. This is one of the reasons why drugs like methadone and buprenorphine are preferred as ways to ease withdrawal symptoms. So continuing on with that, during a withdrawal state, administration of an opioid will rapidly eliminate withdrawal symptoms, as will another opioid, right? Because of those cross-tolerance mechanisms we talked about, since they're all operating through the same channels, using a different opioid than the one that you're coming off of can also eliminate withdrawal symptoms. This elimination of the unpleasant withdrawal state goes back to the concept we've talked about previously of negative reinforcement, right? Negative being the removal of something from the situation, and reinforcement meaning it's going to strengthen the behavior that preceded it. So negative reinforcement in this instance is the removal of the withdrawal state, making it more likely to use that given drug again. So that's that dark side of addiction that we talked about during the drug abuse unit. So in order to examine the specific brain regions that are important for these withdrawal states, opioid antagonists were injected into specific brain regions of animals that were made dependent onto an opioid. And they found that some of these specific brain regions were really, really effective at precipitating withdrawal or causing a withdrawal state to begin. So in particular, injections of opioid antagonists into the locus coeruleus and the para-occipital gray produced dramatic induction of withdrawal symptoms. Keep in mind the locus coeruleus thing because we're going to come back to the norepinephrine angle when we talk about treatment. The nucleus accumbens, as we know, is really, really important for the reinforcing effects of opiates. And what's really, really interesting is it may be important to the aversive stimulus effects and the motivational effects of withdrawal. So if you recall, there's that sort of aversive, strongly emotional aversive component to being in a withdrawal state. By administering an antagonist directly into the nucleus accumbens, not only did that precipitate withdrawal and create an unpleasant state, that was such an aversive event that the animals were conditioned to that event and learned to actually avoid the location in which they were injected. So they formed, if you remember to our previous discussion, they formed a conditioned place aversion to the antagonist being administered. So antagonizing activity in the nucleus accumbens is not only important for withdrawal state, it's highly aversive to the point where animals will learn to avoid that location. So let's talk a little bit about the physiology of withdrawal in terms of what we've been discussing previously. So as the nervous system adapts to a drug, tolerance is produced, right? We've talked about that a number of times already. So you can see here in this sort of schematized figure, we have homeostasis, sort of the state that we're at rest, where we're comfortable. Administration of a drug, an opiate in this instance, produces a disturbed homeostasis, right? Where our resting rate has been moved to some other place. And this is a very broad way of talking about this, right? We're talking about everything from analgesia to sleep patterns to euphoria have been disrupted. So this homeostatic state has been shifted to a different plane. We then undergo a compensatory mechanism which will try to even out the effects of the drug that's being put in, right? So it tries to put us back, our brain tries to put us back to a new steady normal. So then we achieve homeostasis. So as the drug is continuing to be administered, our compensatory mechanisms are keeping a lot of different aspects at the same sort of level. We have a compensation response happening. So then, when this drug is removed from the equation, our compensatory mechanisms aren't so quick to bounce back. These are in place and they take some time to adapt back to our previous homeostatic level. So as a result, we see once again disturbed homeostasis. But we don't see it disturbed in the same way, right? We see this disturbed in this sort of a rebounding opposite direction. So because that neuroadaptation continues to function after the removal of the drug, it's sort of like pulling a rubber band back and then snapping it, letting it go. It's going to go back in the other direction, produce a rebound in the opposite direction that the opiates are pulling. So, for example, the sedative effects of opiate use might rebound back to produce insomnia. So let's talk a little bit more about some specific physiology that has to do with this effect. So changes in cyclic AMP follow this model. If you'll remember, we talked about how opiates produce an inhibitory effect on adenyl cyclase, which is what's producing cyclic AMP. So here we're watching the cyclic AMP that's downstream of opiate signaling. You can see before morphine treatment, we're at a normal level. This graph is showing the percentage of normal cyclic AMP, so of course we're showing 100% of our normal level. As morphine treatment begins, you can see with acute administration, we see a dramatic reduction in cyclic AMP synthesis, right? This makes sense because opiate drugs reduce the effectiveness of that adenyl cyclase, which means we have less cyclic AMP being produced. However, as tolerance develops, we see a gradual increase in cyclic AMP levels in these affected populations. So as our brain begins to compensate for the continued presence of opiates, we see cyclic AMP production ramp back up. So then during dependence, where this drug is being administered regularly, we see that the level of cyclic AMP stays about normal. However, here we have an abrupt withdrawal, where the subject is now abstinent, and the morphine is no longer being administered, we see this huge jump in cyclic AMP levels within the cells, because the brakes that were on this production are suddenly removed, and the compensatory mechanism is still in place, so we have this rocketing up of cyclic AMP levels. And then during the withdrawal state, we see the gradual reduction of these as things sort of go back to normal and eventually return to a normal level. So cyclic AMP production follows this model in the affected areas. Also, we see locus coeruleus firing activity following this model as well, the same sort of reduction in firing during tolerance or during the induction of morphine, then an increase in firing as tolerance develops, and then a massive increase in firing as withdrawal begins. And this is one of the reasons why noradrenergic drugs can be helpful in dealing with withdrawal symptoms, but we'll talk about that more next time. So let's talk briefly about some conditioning of cues, some of the behavioral type tolerance and withdrawal effects that are common. So cues can become secondary reinforcers in themselves. We talked about this at some length in our previous unit, so I won't spend too long on it. But through that sort of learning incentive salience process that we discussed, cues can take on value of their own, and they can start to drive actual physical effects. So these anticipatory reactions can be things like euphoria that's associated with the acquisition or administration activities, or it can result in sort of compensatory responses in preparation of using a drug, which is one of the reasons why addicts are more likely to overdose if they're taking drugs in a novel location without the same sort of rituals or same cues. That anticipatory response doesn't take place. In addition to that aspect, these cues can begin to serve as triggers, which can trigger relapse or a renewed interest in drug-seeking behavior. So this is one of the reasons why treatment programs try to encourage people to leave the old life behind and not go around those old places and see the same old people, because encountering those cues can be powerful triggers for reinstatement of drug-seeking. Likewise, as we mentioned previously, not only can cues be conditioned to rewarding aspects, they can be conditioned to the withdrawal negative aspects. So cues that have been associated with being in a withdrawal state can also promote seeking by prompting a down state. So instead of prompting a euphoric state or something like that with the cues that have been associated with reinforcement, cues that have been associated with a withdrawal state can prompt renewed drug seeking because of the psychological downstate. So there's kind of a general concern that is well founded for the overprescription of opioid drugs, as dependence can develop that leads to withdrawal, even with the best intentions in terms of prescribed use. There's also the concern with overprescription of drugs that there can be significant diversion. And diversion is a term we'll use to mean that it's not being used for, it's either it's on-label use or it's not being used by the person it's prescribed to. So diversion of drugs like OxyContin for recreational use can be highly problematic and have a high societal cost. So using the example of OxyContin, this can be crushed, dissolved, and injected, leading to a much quicker and more powerful administration of the drug, which can lead to addiction. So that's it for this mini lecture. I apologize for running a little bit long on this one, but it all fit best together as one longer video. All right, we'll see you next time.